This is a picture of Beaker, a character from the 80s show called The Muppet Show. He was a lab assistant to Professor Bunsen Honeydew, and Beaker often created chaos in the lab. In this picture, he is testing the fireproof paper they had made. As you can see, it was not fireproof, and the reaction began to get out of control. In this PowerPoint presentation, we will be learning about reaction rates, that is, how fast reactions go, and also about reaction mechanisms, what steps they take. By the end of this lesson, you will understand that the factors affecting rate of reaction can be mathematically expressed. You will know what a zero, first and second order reaction is, and you will understand and investigate the various mechanisms of reaction toward a final reaction and its rate of reaction. You have an accompanying student PowerPoint lesson to print off, which you will fill in as we go along. Feel free to pause the video to fill in your information as we go. In Lesson 6.2, you learned that the rate of reaction depends in part on the concentration of reactants. Increased concentration increases collision frequency. As soon as the reaction begins, products start to form, and the concentration of the reactants decreases. The only accurate data for a relationship between concentration of a reactant and the rate of reaction is at that point where no product is present, at time zero. This is called the initial rate, which is the rate of a chemical reaction at time zero. Products of the reaction are not present, so no reverse reaction can occur. And it is a more accurate method for studying the relationship between concentration of reactant and reaction rate. To determine the initial rate, a tangent is drawn to the curve at time zero, as you can see on this graph. An initial rate is the slope of this tangent line, which is equal to the change in concentration over the change in time. Remember, this is the best way to determine the relationship between concentration of reactants and the rate of reaction, because there is no product present to cause a reverse reaction. To study the effects of concentration on the rate of a reaction, several experiments are carried out. Each reaction starts with a different concentration of reactant. Each of the curves in the graph represent different reactions, each one starting with a different concentration of reactant. Over time, concentration decreases as it is used up to make product. For each curve, the initial rate is calculated. The initial rates are calculated using the slopes of the tangent lines from concentration versus time curves at time zero. Those calculated initial rates are then plotted against starting concentrations. The resulting graph looks like this. Initial rate is plotted on the y-axis, starting concentration on the x-axis, and the resulting graph makes a straight line. This is called a first-order reaction. So if initial rate is plotted on the y-axis and starting concentration on the x-axis, and the result is a straight line, we have a first-order reaction. Recall that the general equation for a straight line is y equals mx plus b. In this case, y equals the initial rate of reaction, m is the slope of the line, x equals the starting concentration, b equals the point at which the line crosses the y-axis, which is 0 in this case, because if concentration equals 0, then rate equals 0. This can also be expressed in these terms as a rate law equation. Rate equals K times the concentration of reactant. Y in the equation of y equals mx plus b is equal to this rate. M in the equation is slope, now represented by this letter K, called the proportionality constant. X in the equation is concentration, now represented by A in square brackets. And B, the y-intercept, equals 0, so it is not shown. This represents a first-order reaction, which simply means that if the concentration of A is doubled, the rate is doubled. If the concentration of A is tripled, the rate is tripled. If the concentration of A is halved, the rate is halved. It is called a first-order reaction because the rate of reaction is directly proportional to the first power of the concentration. Imagine your rate equation above as rate equal to K times concentration of A to the power of 1, the 1 being for a first-order reaction. For reactions with more than one reactant, for example, one that has reactants A and B, if experiments for each reactant produce a straight line, the rate is first order with respect to A and first order with respect to B. Before we look at a specific example, stop and consider this. In many decomposition reactions, the rate of reaction is directly proportional to the concentration of this single reactant because there is just one reactant. In many reactions, there is more than one reactant, so each reactant has its order of reaction determined separately, as in the following example. To determine the rate law equation for a reaction between two reactants, two types of experiments are done. In this example, nitrogen dioxide and fluorine gas are the reactants. The first set of experiments involves reacting excess fluorine with varying amounts of nitrogen dioxide. Excess fluorine is used so that its effect on the rate would be negligible or very, very small. By varying the amounts of nitrogen dioxide, initial rates can be plotted against concentration to see if we get that straight line of a first-order reaction for nitrogen dioxide. The second set of experiments involves reacting excess nitrogen dioxide now with varying amounts of fluorine. Excess nitrogen dioxide is used so that its effect on the rate would be negligible or very, very small. By varying the amounts of fluorine, initial rates can be plotted against concentration to see if we get that straight line of a first-order reaction for fluorine. The data did show a straight line for each reactant, so the data collected demonstrate the rate equation to be rate R equal to K, that proportionality constant, times the concentration of nitrogen dioxide to the power of 1, meaning it's a first-order reaction, times the concentration of fluorine to the power of 1, meaning it's also a first-order reaction. Therefore, the order of reaction with respect to each nitrogen dioxide and fluorine is 1. They are each first-order reactions. However, the overall order of reaction is determined by adding up the order of reactions for each reactant. In this case, 1 for nitrogen dioxide plus 1 for fluorine equals 2. And we say that the reaction is second order overall. Let's look at another example. Decomposition of dinitrogen pentoxide is first order with respect to dinitrogen pentoxide. Remember that straight line relationship between initial rate and concentration is directly proportional. As concentration increases, rate does so as well in the same proportion. If the initial rate of consumption is 2.1 times 10 to the minus 4 moles per liter second, when the initial concentration of dinitrogen pentoxide is 0.40 moles per liter, predict what the initial rate would be if another experiment were performed in which the initial concentration of N2O5 were 0.80 moles per liter. This is how we solve the problem. First, we write the rate law equation for the system. It is R equals K times the concentration of N2O5 to the power of 1. Because it is a first-order reaction, the exponent is 1. We can use ratios to solve this problem because of this directly proportional relationship. Remember, as concentration doubles, so does the rate. The ratio we'll use is 0.8 moles per liter over 0.4 mole per liter, which is equal to our unknown rate for this 0.8 mole per liter concentration over the rate of 2.1 times 10 to the minus 4 moles per liter second for our 0.4 mole per liter concentration. Since this is first order, any change in the concentration of N2O5 will have the same effect on the initial rate of reaction. The concentration of N2O5 is doubled from 0.4 to 0.8 moles per liter, so the rate of consumption will double from 2.1 times 10 to the minus 4 to 4.2 times 10 to the minus 4 moles per liter second. This then is our solution. So far, we have been talking about first-order reactions. We will now look at another order of reaction. Second-order reactions differ from first-order reactions when you plot reaction rate versus concentration. Looking at the reaction rate of chlorine dioxide in this reaction, in which it reacts with hydroxide ions, we get the following graph. The initial rate versus concentration curve is parabolic. That is, it is half a parabola with its vertex at the origin. It is not straight, as in first-order reactions. This means that the reaction rate is proportional to the square of the concentration of chlorine dioxide. Rate equals K times concentration squared. And we say that it is a second-order reaction with respect to this reactant. If the concentration of the reactant is doubled, the rate of the reaction increases by a factor of 2 squared, which equals 4. If the concentration of the reactant is tripled, the rate of reaction increases by 3 squared, which equals 9. Before we look at an example, you should also know that it is possible, but not common, to have zero-order reactions and even fractional orders of reaction. A catalyzed reaction will have an order of 0 when the catalyst is saturated. That is, the reaction would not go faster, even if the concentration is increased, since the catalyst is working full-time already. Let's now look at an example of a second-order reaction. The dimerization reaction of 1,3-butadiene is a second order with respect to C4H6. A dimerization is an addition reaction in which two molecules of the same compound react with each other to give the product. We are asked, if the initial rate of reaction were 32 millimoles per liter minute of C4H6 at a given initial concentration of C4H6, what would be the initial rate of reaction if the initial concentration of C4H6 were doubled? The rate equation for this reaction is R equals K times the concentration of C4H6 squared. This is a second order reaction, so the exponent is 2. Because concentration is squared in a second order reaction, we know that if the initial concentration is doubled, that is multiplied by 2, the initial rate will be multiplied by 2 squared, or 4. This is how we would calculate the rate for a doubled concentration in a second order reaction. The new rate would equal 2 squared times the initial rate of reaction. In this case, it's 32 millimoles per liter minute of C4H6. That equals 128 millimoles per liter minute. To convert to units of moles per liter minute, we would divide that amount by 1,000 or move the decimal place 3 places to the left for a final answer of 0.128 moles per liter minute. I've already mentioned the rate law in this presentation. Simply defined, it shows the relationship between reaction rates and concentration of reactants for the overall reaction. In general, this relationship can be written as follows. Rate equals K times the concentration of A to the power of M times the concentration of B to the power of N, where M equals the order of reaction for reactant A, N equals the order of reaction for reactant B, K equals the rate constant, and M plus N combined equal the order of the overall reaction. So how are these exponents determined? The exponents of the rate law must be determined experimentally. To find the exponent of the rate law, we must study how changes in concentration affect the rate of reaction. For example, if we have a reaction with A and B to make products, the rate relative to the products equals again K times the concentration of A to the power of M times the concentration of B to the power of N. Let's look at a specific example. Recall that the exponents are determined experimentally by studying how changes in concentration affect the rate of reaction. Here again is the example of A plus B making products, and rate equals K times the concentration of A to the power of M times B to the times the concentration of B to the power of N. In an earlier slide, I said that when we have two reactants, we usually keep one in excess and study the other one, and then switch. In the first set of experiments, the concentration of B was kept the same, and the concentration of A was varied. In the second set of experiments, the concentration of A was kept the same, and the concentration of B was varied, and we get this set of data. For a total of 5 experiments, we have the concentration of A for each, the concentration of B for each, and the initial rate for each. In experiments 1 to 3, the concentration of B was kept constant, and A was varied. In experiments 3 to 5, the concentration of A was kept constant, and B was varied. In order to determine the exponent of the rate law, we remember that rate equals K times the concentration of A to the power of M times the concentration of B to the power of N. And to determine the value of M, we use the results from experiments 1, 2, or 3, in which only the concentration of A changes and the concentration of B remains the same. We will use this ratio, this time with rate 2 and rate 1. We could use rate 3 and rate 2. We could also use rate 3 and rate 1. Using the ratio of rate 2 over rate 1, we use the values of 0.4 moles per liter second for rate 2 divided by 0.2 moles per liter second for rate 1. Since we are determining the exponent M and looking only at reactant A particularly, the rate equation is equal to K times the concentration of A to the power of M. This is what the next ratio represents. We have K times the concentration of A for experiment 2, which is 0.2 moles per liter to the power of M, divided by K times the concentration of A for experiment 1, which is 0.10 moles per liter to the power of M. When we solve the left side, dividing 0.4 by 0.2, the units cancel and we are left with the value of 2.0. When we solve the right side, the K's cancel each other, as do the units, and we have 0.20 to the M divided by 0.10 to the M, which equals 2.0 to the power of M. What does this mean? The only way the above equation can be equal is if M equals 1. Therefore, the exponent M of A must be 1. This is a first-order reaction. If the concentration of A is doubled, the rate doubles, as seen between experiments 1 and 2. If the concentration of A is tripled, the rate triples, as seen between experiments 1 and 3. But what about the exponent for B? To determine exponent N, we use the results from experiments 3, 4, or 5, in which only the concentration of B changes and the concentration of A does not change. Then we know that it is the concentration of B that affects the rate. Again, using any two of those experiments where the concentration of B changes, we can compare rates. Using the ratio of rate 4 over rate 3, we use the values of 2.4 mole per liter second for the rate 4 divided by 0.60 moles per liter second for rate 3. Since we are determining the exponent N and looking only at reactant B particularly, the rate equation is equal to K times the concentration of B to the power of N. This is what the next ratio represents. We have K times the concentration of B for experiment 4, which is 0.20 moles per liter to the power of N, divided by K times the concentration of B for experiment 3, which is 0.10 moles per liter to the power of N. When we solve the left side, dividing 2.4 by 0.6, the units cancel and we are left with the value of 4. When we solve the right side, the K's cancel each other, as do the units, and we have 0.20 to the N divided by 0.10 to the N, which equals 2.0 to the power of N. N must equal 2 in order for this statement to be true. What does this mean? The exponent of B must be 2. This is a second-order reaction. If the concentration of B is doubled, the rate increases by a factor of 4, which equals 2 squared. Let's double-check that rate constant for B by using experiments 5 and 3. Pause the video and see if you can determine the exponent N using the data from those two experiments. Here are the equations, rates, and concentrations you need to solve for N. You end up with 9 equals 3 to the power of N, which is only true when N equals 2. This confirms what we solved for in the previous slide, that this is a second-order reaction with respect to reactant B. So far, we have not yet solved for K, the rate constant. Let's do that next. The rate constant K can be calculated from the rate law using our data. We will be using the data from experiment 1. Remember, the rate law is mathematically stated as the rate equals K times the concentration of A to the power of M times the concentration of B to the power of N. In our previous calculations, we determined that M equals 1 and N equals 2, so that the rate for this particular reaction is R equals K times the concentration of A to the power of 1 times the concentration of B to the power of 2. When we rearrange the formula to solve for K, we get K equals rate divided by the concentration of A to the power of 1 times the concentration of B squared. When we put in the data from experiment A, we get the following. Or experiment 1, we get the following. And when we solve, we find that K equals 2.0 times 10 to the 2 liters squared per mole squared per second. Note that the units for the rate constant are going to depend on the order of reaction for each reactant. The rate law for this reaction then is rate equals 2.0 times 10 to the 2 liters squared per mole squared per second times the concentration of A to the power of 1 times the concentration of B to the power of 2. Now we will try the next example. Determine the exponents and K value of the rate law when the following data were measured for the reduction of nitric oxide with hydrogen according to the given equation. You are given the data for 3 experiments. Pause the video while you work through determining the values for M and N. When you're ready to check your results, start the video again. Now you can calculate K. Use the data from experiment number 1. Again, pause the video, do your calculations, and restart when you're ready to check your answer. Now do activity 6.3 on page 382 of your text. So far we have learned about reaction rates. Now we turn our attention to reaction mechanisms and ask the question, how do molecules decompose in order to rearrange? Some molecules can absorb light to decompose the molecule. For some molecules, there must be a collision somewhere to convert enough kinetic energy to potential energy. A collision of 2 molecules is likely, but a collision of 3 at the same time is less likely, and a collision of 4 is very unlikely. Most reactions work in a reaction mechanism made of elementary steps of a collision of 2 molecules, not a simultaneous reaction of 4 or 5 molecules. Just like building a car is a series of single steps, not just one large step, so is a reaction. A reaction mechanism, then, is the series of elementary steps that occur as reactants are converted to products. The decomposition of dinitrogen monoxide here to nitrogen and oxygen does not happen in one single step. It occurs in 2 elementary steps. In step 1, dinitrogen monoxide decomposes to nitrogen gas and an oxygen atom. In step 2, that oxygen atom can then react with another molecule of dinitrogen monoxide to produce nitrogen and oxygen. When the sum of the reactions is taken, the oxygen atoms cancel out, and we are left with the overall reaction. The overall reaction does not show us the steps taken to get to it. A balanced equation does not tell us how the reactants become product. It only tells us the reactant, the product, and the stoichiometry. It gives us no information about the reaction mechanism. In step 2, the oxygen atom is an intermediate. It is neither a reactant nor a product, but formed and consumed during the reaction sequence. It appears briefly in the elementary steps, but not in the balanced equation that represents the overall chemical reaction. Each of the 2 steps is called an elementary step, a reaction whose rate law can be written from its molecules. A reaction mechanism must satisfy 3 requirements. First, the sum of the elementary steps must give the overall balanced equation for the reaction. Second, the elementary steps must involve no more than 3 reactant molecules and usually no more than 2, because a collision of 2 is likely, a collision of 3 is less likely, a collision of 4 is unlikely. To demonstrate this, try throwing 2 balls in the air toward each other. Such a collision is more likely to occur than if you try throwing 3 balls at each other, trying to get them to collide at the same time. With 4 balls, it is even more unlikely, if not impossible. And third, the mechanism must agree with the experimentally determined rate law. All the elementary steps work toward producing the overall reaction. But how do they affect the rate of the overall reaction? It is the slowest elementary step that determines the rate of the overall reaction, and this step is called the rate determining step. In other words, the rate law of a stepwise reaction is rather complex when compared to an elementary reaction. However, there is only one slowest step, the rate determining step in the reaction. The rate determining step controls the overall rate of reaction, as the overall rate cannot proceed any faster than this rate limiting step. Consider the reaction of bread to buttered toast. There are 2 steps. The step 1 is bread to toast, and step 2 is toast to buttered toast. The bread to toast is the rate determining step. It takes 2 minutes. The toast to the buttered toast is quick. It takes a matter of seconds. Let's look at another example of the rate determining step. Again, the rate determining step is the slowest of the elementary steps in a complex reaction. The reaction of 2 moles of nitrogen monoxide with 2 moles of hydrogen produces 1 mole of nitrogen and 2 moles of water. This overall reaction occurs in 3 elementary steps. First, 2 moles of nitrogen monoxide react to form dinitrogen dioxide quickly. Second, that dinitrogen dioxide reacts slowly with hydrogen to produce dinitrogen monoxide and water. Third, the dinitrogen monoxide produced in step 2 reacts quickly with hydrogen to produce nitrogen and water. Step 2 is the rate determining step because it is the slowest of the elementary steps, and the overall rate of the reaction is dependent on this step. In other words, the activation energy for this step will be higher than the activation energy for each of the other steps. What does this look like on a potential energy graph? This is the potential energy graph of the reaction mechanism of the reaction of nitrogen monoxide with hydrogen. This is an example of a stepwise reaction. Each step has its own activation energy. We begin with our reactants on the left. The peak at A represents the activation energy of step 1. The intermediates formed go on to react, and the peak at B represents the activation energy of step 2. The intermediates formed from that reaction go on to react, and the peak at C represents the activation energy of step 3. Step number 2 is the rate determining step, so we will have the highest activation energy. As a rule, the higher the activation energy, the slower the rate of reaction, because more energy is needed to get it going. For any reaction, the reaction mechanism is only a proposed mechanism. Scientists don't always know the exact mechanism pathway, so they are not definitely stated. The problem is that the intermediary molecules cannot be isolated since they are very unstable. They are sometimes detected with a momentary color change. They are only best guesses. Let's look at the proposed reaction mechanism for 2-bromo-2-methylpropane with a hydroxide ion. Experiments show that this reaction is zero order with respect to the hydroxide ion, which means its rate does not depend on hydroxide concentration at all. This can be explained by a two-step mechanism. In the first step, 2-bromo-2-methylpropane slowly ionizes. In the second step, the hydroxide ion forms a covalent bond with the positively charged ion from the first step. This happens extremely fast. It's as if the hydroxide ions are just waiting for positively charged ions to form. The concentration of the hydroxide ion has no effect then on the overall speed of the reaction. The potential energy graph of this reaction mechanism is shown here. See how the activation energy for step 1 is great, as shown by the first orange arrow pointing upward. This is the rate determining step. Notice how small the activation energy is for step 2, as shown by the second small arrow pointing up. And remember that for any reaction, the reaction mechanism is only a proposed mechanism. Scientists don't always know the exact mechanism pathway, so they are not definitely stated. And the problem is that the intermediary molecules cannot be isolated since they are very unstable. Now do questions 2, 4, 6, 10, and 11 on page 387 of your text.